Hello everyone, welcome to the channel Statistica Hub. In this lecture, we'll go through with the topic direct sum and complement and complement and isomorphism. Isomorphism. Okay, let's just see them one by one. Direct sum. So for this, let's just first consider that I have a plane xy. I have this plane xy plane, and I have another plane which is yz plane. Let's like this. This is my yz plane. Okay. Now, if I add these two planes, if I just add these two planes, what will be the resultant? It will be like this. Where this is z, this is y, and this is x. Okay, this is xy plane, this is zy plane, and this is zx plane. So from this, we can say that the sum of these two planes is forming a three-dimensional Euclidean space like this. Okay. Okay, let's say this is my S. The xy plane is depicting by S, and the yz plane is as T. Then the sum of these two, S plus T, is forming R cube. Okay. Now, if I say that there is a vector in R cube, there is a vector in R cube, let's say U, which is as U1, U2, U3, and this belongs to R cube. This vector in R cube can be represented in many ways. Like if I denote it as U1, U2, U0 plus 0, 0, U. I can write this vector, I can break this vector in two forms as U1, U2, 0 plus 0, 0, U3, where let's say this belongs to S and this belongs to T, and the sum of this vector is U. Okay, and I can also write it as the sum of these two vectors as U1, U2 plus 1, 0 plus 0 minus 1 and u3, where this belongs to S and this belongs to T. So this u vector can be written in many ways. Okay, so if I can write this vector u in a unique way, okay, where if I can write this vector u in a unique way, then we say that the sum of these two is the direct sum. Like, let's see it like this, that I have two subspaces S and T. These are two subspaces of space V. Okay, now the sum of these two subspaces, which is S plus T, is said to be direct. That the sum of these two is said to be direct, or you can also say that the sum is said to be S and T are independent. If when if any vector if any vector in S plus T, if there is any vector in S plus T, can be expressed in a unique way as x plus y, where x belongs to S and y belongs to T, then we can say that it is the direct sum. Okay, what did we say? That if there is any vector which is u which belong to this S plus T, then if this u vector can be written in a unique way, which is as x plus y, where this is from vector subspace S and this vector y is from subspace T. Okay, so if the and this is from their resultant S plus T. This is from S plus T, their sum. Okay, now if this u vector can be represented in this sum, like in this format, in a unique way, then we say that it is the direct sum. It is direct sum. Okay, now we already know that if there are two subspaces, which is S and T, subspaces of vector space V, then the intersection of these two subspaces, will also form a subspace. also form a subspace of vector space V. Now I want to know whether the sum of these two subspaces, which is S plus T, is forming a subspace or not. I want to check whether S plus T is forming subspace or not. So for subspace, for checking subspace, what are the two conditions? Which is, first is whether the zero vector belongs to this sum S plus T or not, and the second one is the linear combination, which is as alpha v1. Let's say there is another vector which is v2. Whether this linear combination belong to this S plus T. Okay, so we know that S and T are subspaces. S and T are subspaces. So the zero vector belongs to S and zero vector should also belongs to T. Then the sum of these two, which is 0 plus 0, which is equals to 0. So from this we got that 0 is also belonging to S plus T. Okay, now first condition is satisfied. Now let's check for another one, which is as, let's say I have defined v1 vector as u1 plus w1 and v2 as u2 plus w2. Now the linear combinations of this as alpha v1 plus beta v2, which is equals to alpha u1, alpha u1 plus w1 plus beta u2 plus w2. Okay, and I can write it as alpha u1 plus beta u2 plus beta w1 plus beta, alpha w1 plus beta w2. Okay, where this belongs to S and this belongs to T. And where u1 and u2 are the vectors which belongs to the subspace S, and where w1 and w2 are the vectors which belongs to the subspace T. Okay, so for this is also the linear combination. Okay, so this belongs to S plus T. This is also belonging to S plus T. So from this we got, as it is satisfying the both condition, that S plus W, S plus T, S plus T forms a subspace. It is forming a subspace. Okay. So let's just see the proper definition of the direct sum. Okay. Now let S and T be our subspaces. Okay, of vector space V. Then I can define the direct sum as that S plus T is direct. Okay, and the second one is, I can also say that if S intersection T is equals to 0, because in direct sum we say that S and T are S and T are linearly independent, or you can say independent. S and T are independent. Okay, so for that the intersection should be 0, and we can also say that if X is the vector which belongs to S except 0 and excluding 0, and Y is the vector which belongs to T excluding 0, then X comma Y are linearly independent. Okay, why are we excluding 0? Because if the 0 vector it belongs to this subspace S, then they'll be linearly dependent if this 0 vector belongs to S or 0 vector belongs to T, then they'll be linearly dependent. We have studied this concept in the linear independence and linear dependence lecture. Okay, and we can also define it as, if I can write 0 equals to x plus y, I can define the direct sum as 0 equals to x plus y, where x belongs to S and y belongs to T. Then it means that x equals to 0 and y equals to 0. Why am I saying this? Because if x plus y is equals to 0, it means if I can write that if my x is not equals to 0, let's say if my x is not equals to 0, then x is having some value, let's say x is equals to 5. Okay, then for the whole sum to be 0, that x plus y, for this has to be 0. There is a restriction on y, so that for this to be 0, y should be has to be minus 1. minus 5. Okay, y has to be minus 5. So if I say that my x is not equals to 0, then it will take some value, and that will put a restriction on y, that for the whole sum to be 0, y should be minus 5. Okay, so for this we get that if x is not equals to 0, then our y also is not equals to 0. And from this we got that these will be linearly dependent. But we have said that S and T are the subspaces which are linearly independent. Okay, so this is a contradictory statement. So for removing this contradiction, we will say that the sum of these two will be 0 if they both will be 0. If x equals to 0 and y equals to 0, this will only be the condition, because if one of them will be not equals to 0, then it will put a restriction on the other one. Okay, then our x equals to 0 and y equals to 0. Okay, now I can also say that if I s plus t, the dimension of s plus t is equals to dimension of s plus dimension of t, because the intersection term is 0 here, so the dimension of this will also be 0. Okay, so these five statements are equivalent. I can define direct sum in any of the five ways. Okay, now let's see. So we are saying that I have this vector space V. This is my, let's say this is my vector space V. Vector space V. And this is its subspace. This is the subspace S. Okay. Now there exists a complement of this subspace S. Okay. Complement of subspace S. And what is the complement of the subspace S? This is the area. Let's say this is the complement of subspace S. This is our subspace S, and this is the complement of it. Let's define it as T. Okay, so we can write it as this, that T would be our complement. T would be our complement of S, complement of S, if S plus T is forming the vector space. Okay, if S plus T, where this is plus, this is to denote direct sum. Direct sum. Okay, if I can define this is from the S subspace and this is from T, then I can write T as a complement of S if the direct sum of these two subspaces will form the will form whole vector space V. Then we can say that it is its complement. Let's see it like this, that if S is a line, let's see if this is our line, this is S which is passing to the origin. Okay, if S is this line, then what is its complement? If it is in, let's say, R square vector space, if this is an R square vector space, then what will be the complement of this line? Then any other line which is passing to the origin in the R square, any other line, that's any of these which is passing to the origin is its complement, is the complement of this S. Okay, now if we'll see this in R cube format, okay, in the three-dimensional space, let's say if S is the line which is passing to the origin, then any plane in this, any plane, any sorry, any plane containing containing origin and not containing the S, and not containing this S would be our complement. Okay, this is like this. Let's say if this is my S and this is my vector space, then except this S, all the others are my complement. Okay, now we'll see it more clearly like this. Okay, let's see it like this. Okay, there is a one point to remember, that every subspace has a complement. We can see it like this. This is my, I also said it, that this is my vector space and this is my subspace. Then this will be my complement. This area will be my complement. Okay, so every subspace has a complement. Every subspace has a complement. Now we are saying that this area T is the complement of S. Is the complement of S. Okay, and there is a vector u which belongs to this vector space V. Okay, now this u can be written as x plus y, where x belongs to S and y belongs to T. This is our direct sum. Okay, now this x, what is this x? This x is actually u minus y, and this is said to be the projection of u into S along T. This is defined as this. Okay, so what are we doing? This is the vector space, this is the subspace S, and T is its complement. Then there is a vector u which belongs to this vector space V. We can write it as u as equals to x plus y, where x belongs to this subspace S and y belongs to this subspace T, its complement. Then x equals to u minus y is the projection of u into S along T, and y which is equals to u minus S, this is said to be the projection of u into T along S. Along S, let's see it like this. Let's, S is my even axis. Even axis, this is any axis in R square. Okay, this is my even axis. Okay, and T is some line which I can say, let's say T is my line as E1 E2 comma E1 is equals to E2. This is my line E1 equals to E2. So let's say if this is the origin and this is E2 axis, this is origin, then E1 equals to E2 will somewhere like this. Okay, this is my T, T. Okay, and this is my E1 axis. Now, if this T is the complement of S, this is our S. Okay, this T is the complement of S. Complement of S. If there is a vector u which is equals to minus 1 comma 2 which belongs to R square. Okay, there is a vector u, where will be this point minus 1 comma 2? It will be somewhere like this, minus 1 comma 2. This is u. Okay, now I want to know the projection of u into S along T. What does it mean? It means I want to write this vector x into x plus y, where this is the direct sum, and it is I want to write this vector into the unique format of x plus y. Okay, how will I do this? I know that there is a line which is E1 equals to E2. Okay, now what does it mean that the projection of u into S along T? If I see it geometrically, it means that projection of vector u into S with along parallel to T. Okay, parallel to T. If I draw parallel line to T, okay, parallel line to T, it will project onto S, and this will give me a point which is somewhere like this. Okay, let's say A. This is my point when I project it here. Okay, and if this is my T. This is my T. And these both lines are parallel. These both lines are parallel. So the points corresponding to the y-axis of these are equal. Okay, these points corresponding to y-axis are equal. So this point 2 and this is also 2. This is also 2. This is the point 2. Okay, and as we have the line which is E1 equals to E2. E1 equals to E2. So if my E2 is 2, then my E1 will also be 2. Okay, so this is the point I got, that it is 2 comma 2. Okay, so what would be my x? My x would be minus 1 comma 2 minus 2 comma 2. So from this I got that I have the vector x minus 3 comma 0. That this point will be minus 3 comma 0. So what is this? That I can write this vector u in the sum of these two vectors, which is the direct sum, in the unique format as where x is equals to minus 3 comma 0 and y is equals to 2 comma 2, where x belongs to S and this y belongs to T. And this is said to be the projection of u into S along T. And what is the projection value? The projection value is minus 3 comma 0 here. And if I say it like this, that what will be the projection of u into T? into t on the line t along S, which means I have to draw a line parallel to S. Then we'll draw this line parallel to S, and this will be our point, and it will give us 2 comma 2. So the projection will be here 2 comma 2 here. Okay. So what did I get? I got that if I'll write projection of U into S along T is minus 3 comma 0. This is projection of U onto S along the line T. This is along the line T. This is my line T, and this is my line along the line T. Okay, is minus 3 comma 0, and projection of U into T along the line S is 2 comma 2. Okay, so I have written this vector U in the unique format of x plus y. Then this will be the direct sum. Direct sum. Okay, now let's just say an important example of this. Okay, let's say we have this vector space of r's power 5, and there is a subspace S which is as E1, E2, E3, E4, E5. Okay, with the condition as E1 plus E4 is equals to 0, and 2E1 plus E3 plus E5 is equals to 0. Okay, now for this I have to first find the complement. Okay, I have to find the complement. So for finding the complement, we'll just find the basis first. Okay, so for the basis, let's just find the basis of the subspace. We have studied the concept of the basis earlier. We can just find easily the basis of this subspace as E1 equals to minus E4. Okay, and this will be like E5 equals to minus 2 of E1 minus E3 minus E3. So the basis of these is as, so E1 will be E1, E2, E3, and I can write E4 as minus of E1 and E5 as minus 2 E1 minus E3. Okay, where E1 to E5 belongs to R's power 5. Okay, if I take out E1 common from this, I got 1, 0, 0, minus 1, minus 2 plus E2. It will give me 0, sorry, 0, 1, 0, 0, 0 plus E3, which will be 0, 0, 1, 0, minus 1. Okay, so these are our corresponding bases. These are our corresponding basis vector. Let's just denote them as x1, x2, x3, x3. Okay, so we have these basis vectors as x1, x2, x3 to r's power 5. So for finding the complement, we'll have to extend this basis to r's power 5. And for extension, we have extending the basis, we have studied the concept of extension theorem. Okay, so let's just see if I have the standard basis. I have the standard basis as E1, E2, E3, E4, E5. Okay, and we'll check one by one whether these will form the linear this their okay, sorry, the vectors corresponding to the standard basis will form a linear combination to our corresponding basis or not. Okay, now let's just check for E1 first, whether it is forming a linear combination to our corresponding basis. What are our bases? We have bases as x1, x2, s3, and we are checking for E1 whether it is forming a linear combination or not with these bases. So E1 equals to, with the, let's see, scalars as alpha is, which is alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. So E1 is our 1 0 0 0 0, as it is from r's power 5. Okay, and alpha 1, and what is our x1 basis? Our x1 is 1 0 0 minus 1 minus 2 plus alpha 2, and our x2 vector is 0 1 0 0, sorry, our x2 is 0 0 1 0 minus 1 plus alpha 3. X3 vector is 0 1 0 0 0. Okay, so we'll just find the constant from here. So we'll get alpha 1 equals to 1, alpha 3 equals to 0, alpha 2 equals to 0, and minus of alpha 1 equals to 0, minus of 2 alpha 1 minus alpha 2 equals to 0. So these are the corresponding equations according to this. So from this we can see that I have got alpha 1 equals to 1 and I have also got alpha 1 equals to 0. So this is inconsistent system of equation. Okay, so this will not form the, this will even is not forming the linear combinations of this basis vector. So this is linearly independent. So our new basis will be x1, x2, x3, e1, as e1 is not spanned by this vector. This is our new basis. Okay, so we have got four vectors here. We'll have to extend it one more. So let's check for e2. We'll check for e2 vector whether it is forming basis for that. Okay, e2 equals to alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 plus alpha 4 e1. Okay, and what is our e2 vector? It is 0 1 0 0 0. Okay, and alpha 1 x1 1 0 0 minus 1 minus 2 plus alpha 2 0 0 1 0 minus 1 plus alpha 3, which is 0 1 0 0 0 plus alpha 4, which is equals to 1 0 0 0 0. Okay, you can also say it like this, that the vector e2 is same as the vector x3, so it has to be linearly dependent. Okay, this will form the linear combination, but we'll just check it. So it will be like alpha 1 plus alpha 4 equals to 0, alpha 3 equals to 1, alpha 2 equals to 0, minus of alpha 1 equals to 0, and minus of 2 alpha 1 minus alpha 2 equals to 0. So from this I got alpha 2 equals to 0, alpha 2 equals to alpha 1 equals to 0. Alpha 1 equals to 0, alpha 2 equals to 0, alpha 4 will be 0, alpha 3 equals to 1, and alpha 1 equals to 0. Okay, so this is forming the linear combination. This is forming the linear combination, as this vector e2 is spanned by x1 x2 x3 even. Okay, so the corresponding the vector e2 with this vector will not form the basis. Now we'll check for uh, e3 vector. Okay, so we'll check for e3 vector. Let's just do it here only. So e3 can be written in the linear combination. Okay, now we'll just replace it here. It is like this. We are checking for e3. So what will be the corresponding uh, equations for the e3 vector? E3. Okay, it will give us alpha 1 plus alpha 4 equals to 0, alpha 3 equals to 0, alpha 2 equals to 1, and minus of alpha 1 equals to 0, minus of 2 alpha 1 minus alpha 2 equals to 0. Okay, now we got that alpha 3 equals to 0. Okay, alpha 2 equals to 1, and if I put alpha 2 equals to 1, it will give me a contradictory statement. So these contradictory equations, so these system of equations are inconsistent, so this vector e3 is not spanned by these other vectors. So our new basis will be x1 x2 x3 e1 e3. This will be our new basis. So as we have find our basis, okay, then what will be the complex? Our previous bases are this x1 x2 x3 are previous bases. So this is what, this is our s, is this our s, and this, what will be the complement of s? The complement of s is t, which is spanning set of e1 e3. This is our complement of s. The previous bases are s, and this is the new basis with the addition of the two bases, which is our complement. Okay, because the new basis, the new basis, which is x1, x2, x3, e2, e5. The what are bases? Bases are actually the number of vector which will generate the whole vector space r's power 5, and this is the basis which is the subspace of this r's power 5, and the complement of this is e1, e3. Okay, and the sum of these s plus t is generating r's power 5. Okay, so this will be a complement. So now if I say that I have, let's say I have the vector u, which is 1 1 1 1 1, which belongs to r's power 5, which belongs to this r's power 5. Now I want to know the projection of u into s along t. Projection of u into s along t, what will be that vector? I want to find that vector. So I can write this u, I have to write this u in two unique format as x plus y. That's what we do in the direct sum. Okay, in the unique way. Okay, so I have these bases. I can write this them as that. I can write this vector which belong to this vector space in the linear combination of these bases. This is what we do in the basis concept, that if there is a vector in r's power 5, then this vector can be written in the linear combination of the bases. That's what we do in the basis, that every vector in the vector space can be written in the unique linear combinations of the other of the basis. That's what I can write this vector u as alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 plus uh, alpha 4 e1 plus alpha 5 e3. Okay, and what is this u vector, which is 1 1 1 1 1, and alpha 1 vector x1, which is uh, what is my vector x1, 1 0 0 minus 1 minus 2 plus alpha 2 my vector x2, which is 0 0 1 0 minus 1 plus alpha 3, which is 0 1 0 0 0 plus alpha 4, which is 0 1 0 0 0 0 plus alpha 5, which is 0 0 1 0 0. Okay. Okay, now the corresponding equations to these constants are alpha 1 plus alpha 4 equals to 0. Okay, and alpha 3 equals to 1, alpha 2 plus alpha 5 equals to 1, minus of alpha 1 equals to 1, and minus of 2 alpha 1 minus alpha 2 equals to 1. Okay, so alpha 3 equals to 1 we have got, and alpha 1 equals to minus 1, and from this I can find alpha 2, which will be 1, and alpha 4, which will be 2, and alpha 5, which will be 0. Okay, so this is represented as I have got alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, all values. Okay, so what will be my u? I can write this u in this format, where this is the vector which belong to s, and this is its complement which belongs to t. Okay, so what will be the vector? This vector is, I can write this u as minus of x1 plus x3 plus x5 plus x3 plus x3 plus alpha 4. What is the value of alpha 4? It is 2 plus 2 e1 plus 0 e3. Okay, so I am writing this u vector, which is 1 1 1 1 1, in the format as minus 1 1 1 1 1 plus 2 comma 0 0 0 0, where this vector belongs to s and this vector belongs to t. So this will be my vector projection of u into s along t, and this will be my vector projection of u into t along s. Okay, so what did you get from here? Okay, so I have used the concept of basis here. Okay, you can see it like I have given the vector space s as this, and I have finded the basis corresponding to this vector space, and I have got three basis vectors. Okay, I have got three basis vector, and this would be my first subspace S. Okay, this is my subspace S. These will be my vectors of subspace S, and I have to find the complements of this vector. And because I have to generate S plus T equals to R's power 5, I have to generate the whole vector space, and for that I have to extend these bases to R's power 5, and the additional basis would be my complement. Okay, and I have extended these bases, and the extension of these bases will give me two more vectors, which is E1 and E3, and this is my complement of S. Okay, and you know that any vector, and we have taken a vector which belong to this vector space, that any vector in the vector space can be written in the linear combinations of the basis vector, and I have just noted down that vector in their linear combination. Okay, and by finding the corresponding values of the constant, I have noted down this vector u into the format as this. Okay, where this is my S and this is my T. From this I got the vector S and T, and I can say it like this, that the projection of U into S along T is minus 1, 1, 1, 1, 1, and projection of U into T along S is 2, 0, 0, 0, 0. So what are we doing here is, we have a whole vector space. Okay, and we have this subspace S, and we are taking the complement of this subspace, which is like T. Okay, and we are taking a vector in this vector from the vector space V, and we are writing this vector in the subspace in the format of S plus T, in the format of S plus T, where S is the subspace and T is its complement. So it will generate the whole vector space V. Okay, why are we taking its complement? Because we have to generate, we are taking the vector from the vector space, from the vector space, let's say R's power 5. Okay, and if I got the S, if I have the vector subspace S, which is which is giving me three vectors. Okay, and I have to generate R's power 5, then I have to take the complement of that, that will give me two more vectors. Okay, and the sum of these two vectors will form the whole vector space. Okay, I think you'll get to understand this topic. Okay, now there is one more point. I have done the complements of these vectors as E1 and E3. This complement can be E1 and E4, can be E1 and E5. Okay, so from this we can say that the projection of same vector U, the projection of same vector into U into subspace S, into subspace S, can be different along different complements. Into subspace S can be different along different complements. If I take the complement E1 and E4, then the projection will be different. We'll have different points, and if I take the complement as E1 and E5, it will give me a different projection. It will give me a different vector of S. Okay, so the point here is that we have to first define the complement of a subspace S before finding the projection of any vector. Okay, now there is an important theorem regarding this direct sum and complement topic, which is as, let T be the complement of S. T be the complement of S, and X denote the projection of U into S along T. Let's just say it as P of U. Okay, let's just say it as P of U. That P of U is the denote the projection of U into S along T. Then first thing is that projection of U into T along S is U minus P of U. Okay, this is what we do, that if I have U equals to X plus Y, then Y equals to U minus X will be the corresponding projection of U into T along S. Okay, and the second one is, if U belongs to S, if and only if X is equals to u. Sorry, P of u is equals to u. Okay. Why we say this? Because if u belongs to S, then u can be written as u equals to u plus 0, where this u belongs to S and this 0 belongs to T. Okay. Third point is that u belongs to T only and only if the P of u is equals to 0. It can also be seen like this. And in the previous statement, as if u belongs to T, then it can be written as 0 plus u, where this belongs to S and this belongs to T. Okay. Then the projection of u will be 0. Okay. And the fourth statement is that if that the projection of u equals to projection of u. Okay. And fifth is these are some results actually, that the projection of u plus v is equal to p of u plus p of v, which is projection of u plus v into S along t is equals to projection of u into S along t plus projection of v into S along t. Okay, we can see it like this. This our u vector is like x1 plus y1, and our v vector is as x2 plus y2, where x1 comma x2 belong to S and y1 comma y2 belongs to T. Then the sum of these u plus v will be like x1 plus x2 plus y1 plus y2, where this belongs to S and this belongs to T. So from this we got that the P of u plus v equals to projection of u into S along T and projection of u into S along T. Similarly, we can also say that projection of alpha u, if I multiply this as by a scalar, then it will give me alpha of pu. You can see it like this: if this is u equals to x plus y, then alpha of u equals to alpha of x plus alpha of y, where this belongs to S and this belongs to T. Okay, so these are some results. These are some results. Okay, now let's just see the topic of isomorphism. Actually, this topic is related to the linear transformation or linear mapping. Okay, but we'll just take a rough idea of this topic here because it is an important topic. It will give us different results. Those are very helpful. Okay, so for understanding this, let's just consider two vector spaces. Let's say r's power n and the polynomial vector, which is Pn. Okay, so these are two different vectors, completely different, but these vector spaces have same structure. What? These have same structure. Why am I saying this? Okay, let's say if I have this vector alpha naught alpha 1 to alpha n minus 1, which belongs to r's power n. Okay, which is of r's power n. Okay, and the polynomial, how can I denote the polynomial? We are denoting the polynomial as I equals to 0 to n minus 1, where alpha I t's power I of p's power n. And from this you can see that this vector and the coefficients of this polynomial are same. So if we can associate these two vectors with one-to-one correspondence. With one-to-one correspondence, we can associate these two vectors. Okay, so for isomorphism, we have, let's say we have two vectors as v1 and v2. These are our two vector spaces over same field which is F. Okay, then a mapping from then a mapping T, which is from v1 to v2. We'll understand this topic more in more deep concept in the linear transformation topic, the mapping term. Okay, let's just see. Consider here, I am saying it is as linear mapping. Okay, the mapping of T from V1 to V2 is said to be isomorphism. This mapping is said to be isomorphism. Isomorphism if the mapping is bijective. What if mapping is bijective? We have understand the term of bijective in our very first lecture, which is bijective means it has to be 1 1 and onto. Okay, if the mapping is 1 1 and onto, second is The transformation of x plus y, I can write it as t of x plus t of y for whole xy belongs to v1. And third one is that t of alpha x equals to alpha of tx for all alpha belongs to f and x belongs to vector v1, vector space v1. Okay, then we can say that it is the isomorphism when the transformation is bijective and there is a two vectors x plus y which belong x and y which belong to this vector space. Then the sum of these transformation equals to t of x plus t of y, and by the scalar multiple we can also write as alpha t of x. Okay, so these are the three conditions for two vectors to be isomorphism. The linear mapping of the vectors to be isomorphism. Okay. Now, as this linear mapping T v1 to v2 is bijective. So, as it is bijective, it contains an inverse. So we can also write the inverse of this as T inverse, which will be v2 to v1, and this is what these are linear mappings. Okay, so t is going from v1 to v2, t inverse, the inverse of this, the existence of the inverse from v2 to v1, this is said to be that v1, and then can we say that v1 and v2 are isomorphic. Okay, isomorphic, because the existence of isomorphism of T implies the existence of another isomorphism which is T inverse, then we say that V1 and V2 are isomorphic. Okay, now two vector space. This is the theorem. How can we say that the vector spaces are isomorphism or not? That the two vector spaces over same field F are isomorphic. Isomorphic. First way to check is this, that these three conditions, but we can also check like if these two vectors have same dimension. If these two vectors which are over the same field have the same dimension, then we can say that these vectors are isomorphic. Okay, let's see it by an example. If I am saying that the transformation is from r cube to r cube, the mapping is from r cube to r cube, and the point which is, let's say, 1 2 3 2 3 1 and 3 1 2 is map are mapping to 0 1 1 1 0 1 and 1 1 0. Then if we analyze these vectors which is mapping from r cube to r cube. So from this we got that these vectors are linearly independent. Okay, you can see that these vectors are linearly independent because one cannot be represented in the linear combinations of others. Okay, so these vectors are linearly independent and these have the dimension 3. These have the dimension 3. So these vectors are bases of r cube. Okay, this is the definition of the basis. If my vectors are linearly independent, if they have the dimension 3, then we can say that this is our basis vectors. Okay, and from this we can also see that these vectors are also linearly independent. Okay, and the dimension of these is also 3. The dimension of is also 3. Okay, so these vectors are also the basis of R's power cube. Okay, so from this we got that the domain and codomain space of T are of the same dimension. Okay, this is of dimension 3 and this is also of dimension 3. So these are this transformation T is isomorphism. Isomorphism. Okay. Okay, I think you got it. And now there is an important result which is as V be a vector space of dimension n over, let's say, field f. Okay, over field f, then V is isomorphism of x power n. Let's say how. Let's see how. So we are saying that V be a vector space of dimension n over the field F. Okay, and this vector space V has some basis. Let's say the basis of this V is as u1, u2 to un. This set S. This set S is the corresponding basis of this vector space V. Okay, now what is the basis? These basis can that what is the basis means? That basis means that the every vector of V, let's say V is the every vector of V can be represented in their unique linear combination. Okay, so I can denote this V as, let's say, for AI's fields. Okay, A1 as scalars, A1 U1 plus A2 U2 to AN UN. So if you note that I can write this vector v in the unique linear combination. It means that I can write this vector in the unique n-tuple coordinate vectors. Okay, let's say this is my vs. Okay, this is the coordinate vector of v relative to basis s, that is a1, a2 to an. This is coordinate vector. Coordinate vector that every vector of v can be written in their linear in their unique linear combination, where these are its coordinate vector. Now the coordinate vector, we are denoting the coordinate vector as like this. The coordinate vector in f's power n, that each n tuple, if we take each n-tuple coordinate vector, each n-tuple a1, a2 to a's power n in fn corresponds to a unique vector. Okay, if we take each n-tuple, every n-tuple coordinate vector, this will give us a unique vector. This will give us a unique vector a1 u1 plus a2 u2 to an v un in the vector space v. Okay, so from this we say that the basis s, the basis S induces a one-to-one correspondence, because for every n-tuple, for every different n-tuple, we are getting a different vector. For each n-tuple vectors of coordinate, we are getting a different n-tuple, and from these n-tuples are from the f's power n. Okay, so from this we got that the basis S induces a one-to-one correspondence between the vector space V and the coordinate, then the coordinate vectors, which are from f's power n. Okay, which are from s power n. That for every coordinate, every n-tuple coordinate, we will get a we'll get a unique vector. We'll get a unique linear combinations from the vector which will belong to this vector space V. Okay, so that's why we say that if I have a V which is the vector space of dimension n over the field F, then V is the isomorphism of F. V is the isomorphism of S, because this S, the basis vector, is generating a one-to-one correspondence between the vector space V and field F's power n. Field F's power n. So this is the important result actually for the isomorphism topic. This is very important. Okay, so let's see it. Why we study isomorphism? Why we study this? What do we need? Why do we need this? So an isomorphism image of a vector space maybe is it's actually easier to study or to visualize than the original vector. Okay, but there is one point to remember, that not all the properties of a vector space are reflected in its isomorphic image. Okay, so we are just taking the isomorphic image here. What? Isomorphic image of a vector space or isomorphic image, but this will not generate all the properties of the vector space. There are some it will generate, or it will show all the properties of vector addition, scalar multiplication, but not all of them, like angles, directions. It will not represent those. Okay, so this was all about the topic, direct sum and complements and isomorphism. Thank you.